Hey everybody, Thrasher here. In this video, we are going over the basics of motion, all about describing how things move. We have three key words that we're going to go over, and to be honest, team, the way it's going to work is the first word, speed, because it's so synonymous with everyday life, we're going to spend very little time on that one, spend a little bit more time on the word velocity, and then spend a little more time than that on acceleration. So we're not spending a whole chunk of time for each one equally, they're kind of spread out or they increase as they go. So real quick, speed. You already know what speed is. It's how fast something is moving. Heck, if you either drive or watch your parents drive or play a driving video game, there is a device known as a speedometer, which tells you how fast the car is moving, okay? It is technically the distance an object travels divided by the time. That's what miles per hour means. If you're going, it looks like a little less than 45 miles per hour here. It means you're traveling a distance of 45 miles in a time of about 1 hour. That's what speed is. It's a distance divided by a time. Okay? It's also defined a little more technically for physics where it's a change in an object's position. When you go from one place to another, when you travel a distance, it means you're changing position. We're not really going to use this word so much. Also, quick aside, there's a great movie from the 1990s. Oh my gosh, 1990s Keanu Reeves, before he was famous for like John Wick and his other roles. It was called Speed because he had to keep a bus. He was a police officer. He had to keep a bus over a certain speed. Otherwise, terrible things were going to happen. It's a really bad, but that makes it good action movie. I recommend you check it out. But that's speed. We're in this class going to spend more time using the word velocity. Velocity and speed are very similar. In fact, really the only difference is that velocity is when you're including the direction. It's speed with direction. For example, if you're driving on the road, you're going a certain speed, but driving north on 101 is very different than driving south on 101 or choose your own highway. So velocity actually technically includes direction. Maybe spoiler, in our high school level physics class, the direction part isn't always super necessary. We're not going to use it a whole lot in my class, but we are going to use the word velocity. It is a little more technical in the physics sense. It's the distance an object travels divided by the time, very similar to our definition for speed. Now, because we're going to use the word velocity, that's the equation we're going to focus on, okay? Here it is. Velocity is equal. It is equivalent to the distance an object travels divided by time. That's the equation for velocity. Now, scientists are lazy. They don't want to write out the whole words for these things, so instead we'll use mathematical symbols. The mathematical symbol for velocity is v. That's really easy. The symbol for distance is d and time is t, so this is the same thing. These two things are identical. Velocity is equal to distance divided by time. This is right below just how I would write it in my mediocre handwriting, but again, it's two things being divided. It's the distance the object goes, whether it's a marble or a space shuttle or an asteroid, divided by the time that it takes that object to travel. Now, the nice thing about using equations is this one right here is very much set up for you to calculate velocity. But maybe there's a problem we come across where you are trying to find how far an object travels, the distance. By doing algebra, and you all should have some algebra under your belt if you're in high school level physics, we can solve or we could rearrange this equation to figure out a distance. Or, and this one's a little more technical, you could even solve this equation for time. It's more algebraically a challenge. I do have separate videos reminding us how to do some of these algebra steps. So if you're unsure about how to do this algebra, check some of my other videos. But basically, this equation all by itself is set up to solve for velocity, but we can also solve for other things. Quick thing about how we make measurements, team. In our physics class, we're going to measure distance not with inches, not with feet. We're going to use something called a meter. And we might have already used meters if you're in my class. Kind of depends on when you watch this video. Right here, I have a meter stick. This right here represents 1 meter being held up by this young man. A meter is about 3 feet. It's also very similar to a yard. So if you're familiar with the word of a yard, it's the same thing. For an example, a football field, an American football field, is 100 yards. You have to go at least 100 yards or up to 100 yards to score a touchdown. Well, a yard is almost the same thing as a meter. So on a football field, you got to go about 100 meters. In this class for time, we're going to measure seconds, and that's easy. We're all familiar with seconds. So what is the measurement for velocity? I'm sorry, we're not going to use miles per hour. We're going to use meters and seconds. When I ask what is the measurement for velocity, here's a trick. it's always going to be the measurements of the equation. That's what an equation means. Velocity is equal. It is equivalent to distance divided by time. Distance, we're going to use meters. Time, we're going to use seconds. So the measurement that we're going to use for velocity is meters divided by seconds. Meters divided by seconds. I know you're not familiar with that outside of a science classroom, so it's not the most obvious or intuitive thing, but you'll get used to it, okay? Again, instead of writing out the whole thing in words, we'll use symbols. M for meters, S for seconds. Some real quick conversions. A mile per hour is about half a meter per second, or about 1 meter per second is approximately 2. It's about 2.2 miles per hour. So some quick analogies here. If I'm walking to school, I'm walking at about 1 meter, one of these meter sticks per second. If I'm driving down the highway, I'm going about 30 meters per second. So how to translate between meters per second and miles per hour? Very roughly, you could approximately double it. Okay, again, if you're walking fast, that's about 10 miles an hour, or cut it in half to get to meters per second. Or if you're given a number in meters per second, if you're like, well, how many miles per hour is that? You could roughly double it, and that would give you an approximation, okay? Last topic, team, acceleration. Acceleration is the change in an object's velocity. You are way more familiar with this second sentence right here. It's when you're speeding up and when you're slowing down. A lot of us have some intuition for what acceleration means, especially based on this second little definition right here, but it's also this first one. When an object is changing speed or changing velocity, we say the object is accelerating. Here's a quick animation, a GIF to show you, okay? I have two cars. Both are starting at rest, and then they're moving. Both of them are speeding up. So are they accelerating? Absolutely. They both have an acceleration. Can you tell which one has more acceleration? Yeah, the blue car. How? Well, if we think of this first definition, it's all about an object changing how fast it's going. Both start at rest, 0 velocity, but the blue car seems to end up going faster. It's a little bit ahead right here. So if the blue car ends up going faster at a greater velocity, that must mean it has a greater acceleration, a greater change. That's how we can conclude. So both these cars are accelerating. If the blue car seems to have a greater final velocity, a greater change, it has more acceleration. Now, acceleration is tough to quantify because we don't measure acceleration in our day-to-day life. There's a speedometer on our cars, but there's not something in our cars or bikes that tells us acceleration. So it's not as obvious, okay? We can compare accelerations though, even if we're not familiar with the numbers. One way we can compare is with this, 1g. You may or may not have heard of g's. G is an acceleration when you're falling, when you drop an object, or if you jump off a set of monkey bars or something. When you are just in free fall, that's called 1g. It's related to gravity. It's also related to like how much force you feel from your weight. We're not really going to worry about this part, but when you release something, when something is just falling, it's 1g. Okay, let's compare that to a couple of other things, all right? First, sticking with free fall, I was fortunate enough to travel to New Zealand years ago, and I went skydiving. When you are free falling, when you are skydiving, you have an acceleration of 1g. I've also gone bungee jumping, and same thing. When you are in free fall, when you're just falling through the air, when Earth is just pulling you down, that's an acceleration equal to 1g. Maybe you've been to a fair or an amusement park and they have this ride called the Gravitron, or it might have some other name. You kind of sit up against the wall and the ride spins around and you kind of feel yourself pressed against the wall. When you're feeling that pressing against the wall, you are being accelerated. That ride has an acceleration of about 3 Gs. It's about 3 times as intense as just free falling, okay? There's also some roller coasters, and some in particular are well known for their acceleration. This roller coaster right here is actually down near Los Angeles. It's in a place called Knott's Berry Farm. It's called the Accelerator. It accelerates you at about 4 Gs. Let's watch this short video.
To the accelerator, please keep your head against the headrest, hold on tight to those ground bars, keep your feet flat on the ground, and goodbye.
Oh man, I don't know if the audio translated, I hope it does, but even if not, you could see that that roller coaster accelerated. That acceleration was about 4 Gs, or 4 times as much as something that's in free fall. Like modern times right now, maybe you're familiar with the ideas that like Teslas and electric cars can accelerate very rapidly. It's very impressive. A Tesla Plaid accelerates at, I think, about 1.2 or 1.3 maybe Gs. Very impressive, so a little faster than things free fall, okay? Team, a car crash. This is my last example. When you have a car that slams into something, it changes its speed. It slows down. A change in velocity or slowing down. Again, that's an acceleration. And hopefully it's not something any of us experience, but a severe car crash will experience an amount of acceleration equal to, man, look at this, about 50 Gs. That's a major car crash, okay? This is technically maybe known as a deceleration, but it is a type of acceleration. So a range of ways that objects accelerate, from just dropping and under free fall to different rides. These are how objects may accelerate that we might experience, okay? My last little bit, we're almost done with this video. There is an equation for acceleration. Here's more definitions again. The equation matches this first definition at the top. Acceleration is when velocity changes. So the equation for acceleration, it says acceleration is equal to, look at the top, now I have a fraction. I have two things divided. The top is this change in velocity. I'm subtracting, I'm comparing the object's final velocity, how fast it ends up going, compared to the velocity it started with, the initial. So this equation is more complicated than the last one. We have a fraction, that makes it a little tougher. And then on top, we have to do a little bit of subtraction. And then what are we dividing by? We're dividing by the time, because changing speed, changing velocity, it takes a little bit of time. What I have in orange, it's the exact same equation. It's simplifying things. Again, scientists are lazy. I don't want to write this whole thing out, so instead of acceleration, I'm going to use the symbol A. For velocity, we're going to use that symbol V. For final, we could use what's known as like a subscript. You kind of write it a little bit below. In fact, scientists are so lazy, they don't even like to write it like this. You're going to see me often write it this way. Acceleration is equal, it's a fraction. It's the final velocity minus the initial velocity. You divide that by time, so a little tougher. Right? Again, in my mediocre handwriting, this is how I'll write it. But it's the same thing from the last slide. Acceleration is equal to, you gotta first subtract velocities. Sometimes one of these might be 0 to make it easier, but not always. You then divide that by the time. Real quick, if you look at a textbook or go online, you might see acceleration written like this, where there's this triangle symbol. We're not really going to use this symbol in my class, not right now at least. The triangle symbol, that's uppercase Greek letter delta, it means change. It means subtract. So these two things are the same thing. We're really going to use this, at least in my own class, but you might see it like that later on, okay? How do we measure acceleration? Again, it's not something we see very often in our day-to-day lives, so it's not the most intuitive thing. But remember what I said earlier. The way we measure is equal to the equation. We have velocity divided by time here. On top, it's velocity. Hopefully you remember, because I talked about it a little while ago, the unit for velocity is meters per second. So that's the top part. We're still dividing. On the bottom is time. Do you remember what's the measurement for time? That's seconds. So this is weird, but this right here is the measurement for acceleration. M divided by S, divided by S. Okay, I just rewrote it right here. I'm not going to go over this, but you could actually do a little bit of algebra with how this is written, and you could rewrite it like this. Either of these are fine. You're going to see that it's more common to write it this way, but both are actually valid. This one right here, you would read this as meters per second per second. Meters per second per second. Or meters per second squared. And I've written both those out just like that. This is what we're going to attach whenever we make a measurement or do a calculation for acceleration. My last slide, I hope you were taking notes. Notes help us internalize what we're learning, so it's always recommended. But on the bright side, your teacher, and if you're in my class, I certainly do, have resources that will have these core notes in them. So you don't have to memorize these exactly just based on the video. You'll be getting notes, or you'll see notes, you'll see it in a textbook that has these definitions. This is an example of what I've given my classes in past years. But that's it. That's us going over the 3 core ways we describe motion. Thanks a lot for watching.